Hello and welcome to another tutorial. In this tutorial I'm going to continue our discussion on root finding algorithms, and after looking at different root finding methods, to recap, we looked at the general lemma of root bracketing, which states that if we have a continuous function and f of a times f of b is negative, or the function changes sign from the initial position of the interval to the endpoint, then it must have at least one root in this interval. And this interval is then called a root bracket, which means we have one root in this interval. And we looked at the bisection, trisection, secant and improved secant method, Brent's method, Newton's method, but there's also another method called generalized Taylor method, which we might look into this method, generalized Taylor method, but it's not a common method. It's rarely used. And so we looked at the binary search, we looked at the trisection, we looked at the secant, improved secant, we looked at the Brent's method, we looked at Newton's method, and now what we're going to do, we're going to look at the comparison of the methods. So let's say we have a polynomial, f of x equals x squared, x minus 2 squared, x minus 3 times x minus 4. So in general, this polynomial has a degree of 6. So it should have 6 roots. And in this specific case, all the roots are real. 2 of them, which is 0 and 2, have a multiplicity of 2. So we have 2 roots at 0, 2 roots at 2, 1 root at 3, and 1 root at 4. Alright? Now the reason I'm looking at the polynomial is because of that. If we look at the performance of these methods with respect to finding the roots of a polynomial, then because we know that any function can be locally expanded as a polynomial, this is the Taylor's theorem, then if we have an algorithm that works fine for polynomials, then it should also work fine with the functions, with the general nonlinear function, as long as the initial bracket of the root is small enough so that we can be able to expand the function into a Taylor polynomial. Okay. Now, one of the first thing that we can do with this polynomial is to visually look at the behavior of the function. Okay, and the way I'm going to do it is like this. So we already know the roots, right? 0, 2, 3, and 4. And the behavior at 0 is 0 squared, right? So it should be something like this black curve, x squared. At x minus 2 squared, it's also a behavior such as x squared, right? But then the question is it going up or down at 0 and 2? And that depends on the incoming value of the function. So at minus infinity, we know that this term is positive, x minus 2 squared is positive, x minus 3 is negative, and x minus 4 is also negative. So the whole function is positive. So the function at minus infinity starts from the plus infinity and comes down, right? So at x equals 0, the behavior is x squared and it should face up. Now another way is just to look at the f double prime. And f double prime for this term is 2, which is constant. Then the value, and so then the concavity depends on the sign of this rest. The rest at 0, which is positive, right? So if I evaluate this part at 0, it's 4 times minus 3 times minus 4, so it's positive, so the function faces up. But typically for polynomials, I use the first method. I just look at the behavior x squared and I say, okay, it has to either face up or down. and that depends on how the function starts from minus infinity and whether or not it's positive or negative, okay, at minus infinity. So here the function is positive, so it should come here and then goes up again, and then it has to come down again because at 2 it's 0, right? So for it to come down, the behavior of the function at x equals 2 must face up, okay? So it comes down, becomes 0, and then has to go up again, and then at 3 it's 0 again, so it has to come down. So the behavior of function at x equals 3, which is a linear function, the question is whether it's this way or in the positive way, and here it has to be in the negative way. And you can confirm that by basically finding the value of the function, the rest of the polynomial, x squared, x minus 2 squared, x minus 4 at x equals 3. And this is positive at 3, this is positive, x minus 4 is negative, so the slope is negative. So it comes down, then has to go up again because at 4 it's 0, and you can probably guess that it has to be a positive linear behavior, positive slope. So we can readily look at the behavior of this polynomial. 2 roots, simple roots, 2 tangent roots, so even roots. And if you recall, we mentioned that bisection and trisection are based on pure bracketing and nothing else. So bracketing and binary search or ternary search, so they are guaranteed to converge if there is in fact a root in the initial search for so the limitation here in the bisection and trisection was that the original search interval must also be a bracket. So for example, for this polynomial, if I start from minus 1 to 5, the function is both positive, so it's not a valid bracket to find a single root. But then we said that, okay, if I want to find all the roots, what I can do is to divide the initial interval, even if it's not a valid bracket, into very small sub-intervals and try to run the binary search in each sub-interval, okay? So here we're interested in finding all the roots, in the interval, let's say minus 1 to 6, which is not a valid bracket, right? But we don't care because we're dividing into sub-intervals. For the secant, we said that it's faster than bisection and trisection, but there is no guarantee that it's going to converge. For Brent, the same thing, it's faster than secant, but there is no guarantee that it's going to converge. For Newton, it's faster than Brent, and the difference from the difference of Newton with the rest was that in Newton we don't really need a start interval, we just need a start point that is close enough to the root, okay? So Newton is the fastest, it is faster than Brent, but there is no guarantee that it's going to converge. And we look at some of the cases where the Newton's method failed. Obviously, when the slope becomes 0 at some iteration point. Now the other thing is that bisection and trisection, they fail at even roots or the roots that are tangent, because no matter how small the interval is around the root, you can never have a valid bracket because the function has the same sign about the root, right? So there is never a valid bracket, and these two, bisection and trisection, are purely based on bracketing, so they're going to fail. So if we go to Eclipse and try to test this polynomial with bisection or trisection, we most likely are not going to be able to find the root at 0 and the root at 2. Alright, let's head to Eclipse and try to look at all these different methods. So in the Eclipse, in our demo roots project, I'm going to create a class, test all methods, and I'm adding a main method here. public static void test1 or test bisection, test bisection. Okay, so I'm going to first start with the bisection. Now if you recall the way we're going to do it, for bisection we don't need the derivative, so I'm going to use this interface, real root function, and I'm going to call it func, and x goes to x squared times x minus 2 times x minus 2 times x minus 3 times x minus 4. Okay, and then we create a real root object, we call it root finder, new real root, and I'm going to pass in the function, the real root function. And if you notice, I use a lambda expression, which is very convenient. And then I'm going to create a list of doubles and roots, root finder dot bisection. If you recall, we had a method from start and end, start end with the initial guess, and this one that returns a list, start, end, and number of sub intervals. So we're going to search in -1 to 6 and 1000 sub intervals, or maybe 100. So if you notice, -1 and 6 is not a valid bracket because this function is positive at both ends, but because we're searching into sub intervals, we don't really care if the initial search interval is a bracket. Now let's import the list object from the Java utils. Alright, now at the end we're going to print the roots, system.out.println roots, and we are going to also plot the function. So in order to plot it, I'm going to create a Matlab chart, which is in my Matlab in the plotting package, in the plot package. Fig new Matlab chart, and let's import it from the matlab.plot, and then I'm going to create the x values. Double x is I'm going to use the linear space function in mathutils from -1 to 6, 1000, and double y. I'm going to apply the function to the array, so I call the array func object, apply func to the x. It's just a simple for loop, and then real function, so the interface is not the same, so I'm going to say t goes to func dot value at t. So this way I use this interface to implement another interface using the lambda expression, which is very convenient. And then we're going to fig.plot x and y, fig.plot. So I'm going to write this, plot this with the blue color, and then I'm going to have another plot for just the line that is basically y equals 0. So double x1 is -1 and 6, double y1 is 0 and 0. I'm going to plot x1, y1 with a color of red and dotted lines, and then fig.render plot, fig.run with a system exit flag true. So if I test this, it finds 3 and 4 as we expected. It doesn't find 0 and 1 because these are tangents, and in order to show the plot I have to go to the run configuration. Because I'm using a Mac, I have to remove the check for this flag. As you can see, we indeed have 4 roots. One is here, one is here at 0, one is at 2, one is at 3, and one is at 4. And this is basically the same shape as we had here, right? So that's one way of just trying to quickly look at the shape of the polynomial, by just finding the roots, also the types of the roots. Okay, so the bisection fails to find 0 and 2, the even roots, because no matter how hard it tries or how many subintervals we have, we can never have a valid bracket for 0 and 2, because they are even roots. The function doesn't change sign, right? So let's try trisection. So test trisection. Instead of bisection, I'm going to call test trisection. And here I'm going to call the trisection method with the subinterval. So -1 to 6, 100. Again, trisection and bisection run based on the same philosophy of root bracketing. So this also should fail to get the 3 and 4, 0 and 1. So we only can find 3 and 4, which are simple roots, right? This is a simple root, this is a simple root, this is a tangent root, and even order, and even order. So it fails. So bisection and trisection so far fail. And the next is secant, which, if you recall, we improved it. So test secant. And here I'm going to call the secant method. We have 2, one with a start and end that returns 1 double value, and one with a start and end and number of subintervals that returns a list of roots. So -1, 6, 100. So the secant here also fails. The behavior of the secant is really not, we cannot say for sure whether or not it fails, or it fails at the even roots. But what happens if we increase the number of subintervals to 1000? It still fails. So it appears that the secant fails here no matter what. What if we change the interval -2 to 6, 0, 2, 3, 4? Now it can find 0 and 2. And so it appears that the success of the secant method is not guaranteed at all roots, no matter how many subintervals we have, and it mostly depends on the initial and the initial interval that we search for the roots, which is not good, because all we want is to start with an interval that has all the roots, and the method should be able to find all the roots, which we definitely see that the secant is not able to find all the roots in the -1 to 6 interval. If I increase it to -4 to 6, it is able to find the root, all the roots. So one negative point for secant for not being able to find all the roots over -1 to 6. So after the secant, we're going to test brent. Now brent is one of the good methods, so we have a lot of hopes for brent in the fact that it should easily be able to find all the roots. Let's see. So here I'm going to do this brent. We have 3 methods: start, end, number of subintervals, start, end, and guess. So this one returns all the roots, -1 to 6 with 100 sub-intervals. Yes, it is able to find all the roots. As you can see, it doesn't find them in the sorted order, so it finds 0 first. So it finds 0 and then finds 3 and then finds 2 and 4. But it's able to find all the roots. So even if I change to -4 to 6, still the same, 0, e -9, it's basically 0, and then 1.99, this is 2, and then 3 and 4. So Brent is, so far Brent is the best. And let's look at the Newton. Test Newton. We also have a lot of hopes for Newton because it's a fast algorithm and it doesn't care about the bracketing or any of that stuff. So we hope that it's also going to find all the roots just like Brent and even faster. So here I should call the Newton method start end sub-intervals -1, 6, sub-intervals 100, and max iterations I'm going to set them 1 to 100. Unfortunately, the Newton fails to find the 0 and 2, which is very displeasing because we had a lot of hopes for the Newton's method. What if I increase 1000 sub-intervals? No, it's still not able to find. And what if I set to -2 to 6? It's still not able to find all the roots. -5 to 6. No, it's still not able. 1000 iterations, still not able. So unfortunately, Newton also fails in this test to find all the roots, and that's very unsatisfactory. Let's go and have a look at the Newton's method. If you recall, in the Newton we have 2 relative errors and the absolute error for the convergence test, and apparently none of them can succeed in resulting in the finding the roots. What if we, right now we're using absolute error and relative error of 10 to the -15. What if we set it to 10 to the -12? Let's see if the Newton is able. Now it can find 2, 3 and 4, still cannot find 0. So if we reduce the relative error to 1e10, so 4, 3, 2, 2, 2, 2, 2. So now it's able to find 4, 3 and 2, and obviously we see some repetition here, which is expected because we have multiple sub-intervals that may converge to the same root, but it still cannot find 0. So Newton really fails compared to Brent here. So what we conclude here is that although Newton could be in fact faster than the rest of the methods, but Brent seems to be most reliable for this type of cases. So I'm going to head back to real root and set the errors to 1e15. Okay, so let's try Brent one more time. It is able to easily find all the roots. So my recommendation is try to use the Brent method, or try to add more convergence or test to the Newton method to make it more reliable. Thank you for watching, and I'll see you in the next video.